Saxon Advanced Mathematics, lesson 38. It's a two-parter. It's a three-parter. All algebra. The first one is technically statistics. The topic is permutations, which is one that many students enjoy. I hope you are one of them. Example 38.1. I'll review how to do these in the first problem, which is pretty basic. How many different ways can the numbers 3, 5, 7, and 8 be arranged in order if no repetition is permitted? Okay, so the best way I can explain for you to think about this is that you have like Scrabble tiles, only they have numbers on them. 3, 5, 7, and 8. How many different ways can you rearrange these tiles? Okay, so imagine that you have like a tray that those things fit in. Those tiles. So there's 4 boxes in this tray, and these tiles are going to fit in there. I know my picture does not make it look like they would actually fit, but pretend, okay? When you go to fill in the first tray, you can put in any one of those numbers. So you have 4 choices as to which ones to put in here. Okay, then you go to fill the second tray. Now, one of these has been used up. It doesn't matter which one you used up, but you can agree with me that there are only going to be 3 choices left. And then when you go to fill in the second one, there will only be 2 choices left. And then for the very last one, there's only 1 tile left. So there's only 1 choice left. All right? The way that we calculate this is to multiply them. 4 times 3 times 2 times 1. And that equals 24 ways. Now, one important word, or I guess it's technically 2, that John put in this problem is he said no repetition. We did not have an endless stack of tiles with 3s on it, or 5s or 7s or 8s, so that we could, we couldn't create the number 3333, for example, or 5555. We couldn't repeat any of them. In these problems, John is going to play back and forth with that idea of, are we allowed to repeat the elements or not? I think we played with that last year, but we'll play with it more this year. 38.2. Oops. How many 4-letter signs can be made from the letters in the word equal if repetition is permitted? So it's a very important part of the problem is telling us, can you repeat or not? Now, in these, we can repeat. And John says that we're making 4-letter signs. So even though we have 5 different, imagine there are stacks of Scrabble tiles, right? A whole bunch of them, really tall. But we're only filling in a tray with 4 places rather. Again. Pretend these are like Scrabble tiles and we can fit them into this tray. There's only 4 slots in the tray because we're making 4-letter words and we're allowed to repeat. So when we go to fill in the first one, we can put in any one of these letters, right? So we have 5 choices. When we go to the second one, we've chosen, let's just say we chose the E to put in there, but there's more E's in the stack because repetition is permitted. So that means when we go to fill in the second letter, we still have 5 choices, and we still have 5 choices, and we still have 5 choices. So that means that when we calculate the number of ways we can combine these letters, remember the number of ways means permutations, that means there are 625 ways we can arrange those letters. Interesting, right? I mean, maybe not, but pretend. 38.3. A multiple choice test has 8 questions and there are 4 possible choices to each question. All right. How many different sets of answers is possible? Now, John doesn't tell us if there's repetition or not. So we're going to have to use logic to figure it out. First, let's draw our sample size, if you will. Okay, this is our test. There are 8 different questions. So we have 8 different opportunities to make a choice, right? Now, when we sit down and do the first question, there are going to be 4 choices after it, right? So that means we can choose any one of those 4. So we have 4 choices we can make. Now, when we go to take the second test item, have any of our choices gone away? No, there will be 4 new multiple choice options for us. So we can see that this test implies that there's repetition, right? It's not like you only have one set of answers and you're using them up. Each time we look at another question, we'll have 4 choices. So every single one of the 8 questions will have 4 choices. And when we go to multiply this, it'll be equal to 4 to the 8th. This would be a perfectly fine answer. I went ahead and did the calculation and found that it was 65,536 different ways that test could be scored. And P.S., this is why teachers always know if students are cheating. I mean, this is a pretty short test. There's only 8 questions on it. But look at how unusual it would be that the same student would get all the same answers, unless they were all right? I mean, that would be one thing. But if a student had, say 2 or 3 of these wrong, but it was exactly the same as another student, that would be kind of surprising. I don't know. That would make a lot of teachers very suspicious, unless like the questions were poorly worded or something, I don't know. But you can see that there are many different ways that students could score a test like this. Ready for another one? One more, and then we switch topics. Example 38.4. Oh, the moral of the story I wanted to say about that multiple test choice problem too is that sometimes John does not overtly tell us, oh, repetition is permitted or it's not. We have to use logic to come to our own conclusions. How many 3-letter signs can be made from the letters in the word numeral if no repetition is permitted? I usually write no rep or yes rep once I get into these to remind myself. No repetition is permitted. We've got 3-letter signs. So we've got a lot more letters to choose from. Oh, shoot. I'll make it bigger. We've got a lot more letters to choose from than we need. So let's think about that. Let's see. There's 1, 2, 3, 4, 5, 6, 7 different letters to choose from. So when we fill in our first square, we could put any one of the 7 in. Now, we're not allowed to repeat, so this is 6 and this is 5, right? Because we'll have 1 less letter. We still have lots of choices, though. And so then we multiply. And we find out there are 210 ways that we can arrange those letters. Yay! Okay? The tricky thing about permutation problems is that you have to use common sense and logic with each individual situation. There isn't a general rule that always works as to how to set them up and fill in the numbers. You have to think about each and every one. That makes some students crazy, but to some, that's the fun of it. You can guess which camp I'm in. Designated routes. When you were a little kid, did you ever walk around backwards just for the sheer joy of it? That's what we're going to do here. We're just going to work backwards. Let me show you something that you know. X squared plus 3x. That is a quadratic equation. And that, I am convinced, you can solve by inspection. We don't need to drag out the man-eating dragon or complete the square. We can simply factor it. Let's see, it'll be 2 numbers that multiply to this and add to this. I'll give you a second to think of them and then I'll write them in. We know it's like that, right? right? They multiply here, they add to that. And we know that because of the zero factor theorem, that either x plus 7 equals 0 or x minus 4 equals 0, right? If two things multiplied together equal 0, then one or the other has to be 0. Do a quick little algebra dance here, and we get x equals minus 7 and x equals positive 4. Now, what we're going to do is, instead of going in this direction, where here we're solving for the roots, here, this we call the solution, right? Or we also find the roots. This is the answer. Let me just put the box around it. What we're gonna do is we're gonna be given the roots, and we're gonna go backwards and turn them back into the equation. That's kind of weird, isn't it? The way that we'll do that is to remember that when we have the answer, we can rewrite the terms of it by changing the sign, right? Here we switched the sign as we simplified it. So we know that this one would be x plus 7, the opposite of that sign, times x minus 4. And then we could multiply that to get x squared plus 3x minus 28, because I add these for the b term and I multiply these for that term. And this would be our answer. Oh, equals 0. I didn't write that, but that we would add that on too. All right, so that's what we're going to practice doing. We're going to take these. We're going to remember that you take the value of the root and you change the sign on it, and then that's what you put in the binomial. Let's do a practice problem. And there are 2 of these. And then we have one more topic. Lord have mercy, John. 38.5. We already did 4 problems. That seems like a lot. Okay, John says to us, write the quadratic equation with a lead coefficient of 1. I'll explain that at the end. Whose roots are minus 3 over 5 and 1/2. Now these are a little trickier than what we had in my example because these have fractions in them. So let's remember, let's use the same rule though. We know that x, and sometimes it's fun to do it like this, x minus 3 over 5. That'll help us get the roots, the signs right. Right? We take x and we subtract the roots, x minus that, and those create the 2 binomials that we can then multiply together. So now what I'm going to do is I'm going to rewrite this x plus, oh that should be a 5, sorry, x plus 3 over 5, and then x minus 1/2. We're going to multiply those binomials, right? X squared plus 3/5 x minus 1/2 x. Well, we have a little bit of a mess there. We'll fix that later. And then this will be minus 3 over 10, right? We're going to have to fix these. This one will multiply by 2 over 2, this one by 5 over 5, right? We're just least common denominatoring. So this becomes 6 over 10x, and this becomes, and it's minus 5 over 10x. So our final answer is x squared. This I don't need to look at because it came down to right here. So it's plus 1 over 10x minus 3 over 10, and then we add equals 0. This is our final answer. Now, You might look at this and go, I don't like these denominators. I want to multiply every term by 10 in order to make the denominators go away. But that's what John means when he says that he wants a lead coefficient of 1. He's saying, I don't want you to get rid of the fractions. I want this x squared term to have a lead coefficient of 1, which is invisible. So he wants it to be left like this. He doesn't want you to fool around with getting rid of those fractions. So this is our final answer. I mean, that's cool, right? Let's do another one. There's one more of these. (38.6). Ready? Write the quadratic equation with a lead coefficient of 1. Okay, so we'll leave the fractions as they are. Whose roots are you ready for this? 1 plus the square root of 2. Let's put it in parentheses, that'll help us. And the other one is 1 minus the square root of 2. Okay, so we remember our simple formula. It's x minus the first point times x minus the second point, or value, it's not really a point, right? These are the roots. So we just use x minus, and then we'll multiply, but these we have to simplify first because, look at there's minuses in front of the parentheses. So this is going to become x minus 1 minus the square root of 2, and this is going to become x minus 1 plus the square root of 2. You with me? That's kind of grotesque and ugly, right? But when you have a binomial, make sure you put it in parentheses, subtract it, and then clean up what happened to that crazy, what happens when you apply the minus sign. All right, so now we're gonna multiply these guys together, doing the dance. X squared minus x minus square root of 2 times x. Second one, minus x minus x plus 1. I don't want to combine that with this radical. Plus 1 plus, oh no, this times this would be plus the square root of 2. Now it's her term. Plus the square root of 2x. Oh, I like that. That's going to cancel. Minus the square root of 2. Notice how I'm just matching them up, right? Minus the square root of 2. And then this will be minus square root of 2 times the square root of 2 will equal 2. So I'm going to put it here. I don't need it down there, right? So what I'm doing is I'm just creating columns. Oh, I forgot to put the square on that. I'm sorry. I'm creating columns. Whenever I create a new term, I put it in its own column. And then when I'm multiplying later in the game, whatever product I get, I just look for something that matches to it. And now look what happens. Cancel-y, cancel-y. So I get x squared minus 2x minus 1 equals 0. And that's the right answer. It's crazy, right? So we're working from the solution back up to the quadratic. We remember that the trick is to rewrite it, and I should put this equals 0. The trick is to say x minus whatever that is. And that's all there is to it. Isn't that just easy and fun? No, those are challenging problems, and it's the whole walking backwards thing. It always feels weird to do stuff backwards. Okay, the next final part, there's 2 problems, and they are rate problems. Oh, goody, right? Overall, average rate. These are the favorites of many writers of standardized tests. Overall average rate. Okay, Remember that distance equals rate times time. And we can change that around to say rate equals distance divided by time. I'm just dividing away the t. Or we can say time equals distance divided by rate. So we want to have all three of these tools at our disposal. And then I want to give you one more idea. The overall rate, average, oh wait, I don't want to write it here, it's too little. The overall average rate will equal the overall distance divided by the overall time. Now, that is just taking this and adding overall to every word, but it's going to become quite useful in doing these problems when we start to get turned on our heads, right? All right, let's try one. Is this one of the examples? You're like, dude, why are you asking me? Yes, it is. It's 38.7. I'm probably going to run out of room, but you know, that's a problem for in a few minutes. All right. Again, they often tell us, they're going to tell us two different scenarios, and then we're going to come up with the overall averages. Frank and Judy drive for 100 miles, that's our distance, at 50 mph, so that's their rate. Okay? Now, we can figure out from this that this is their distance, this is their rate. What would their time be? Oh, it's the distance divided by the rate. So the time would be equal to 2 hours. And it's also often helpful to put ones on these because we're going to get another scenario in just a minute. And here it comes. The second scenario is that then they drove 180 miles. That's the second distance. I'll scoot up a little so you can see better at the bottom. At a rate of 60 miles per hour. So their second time, again, time is equal to distance divided by rate. Everything's set up. So their second time is equal to 3 hours. All right. Now we can see that and we want to find, and it says, what was Frank and Judy's overall rate over the whole trip? The overall average rate is the overall distance between the overall time. So I'll calculate in here the overall distance equals 280 divided by the overall time, which would be 5. 280 divided by 5 equals, I'll just give you a spoiler. Gracie just came in from outside. She's freezing cold. It's 2 o'clock in the morning, by the way. Her nose is wet and icy, and I have on short sleeves, and she keeps rubbing her freezing cold nose along my arm. And you know, she definitely wants my attention, and she's getting it right now because I'm petting her as I talk. Grace, this is a riveting problem, and I really need to finish it. Are you okay with that? She said no. So 280 over 5 means that the overall rate equals, let's see, 56. I just divided that in my head as best I could. The overall rate equals 56, squeeze it in, mph. Compared to some of the other rate problems we've had, these are pussycats. But it's still a lot to think about, right? So remember that this formula is going to help you at the end. Let's do another one. And I think there's just one more, 38.8. Yes. This is a long lesson. You've been very patient. Let's bring it down. 38.8, it's Frank and Judy again. This time, they have 3 legs to their trip. So here we go. 1, Frank and Judy drive for 100 miles. D equals 100 miles at 50 miles per hour. Rate equals 50 mph. And I'll just remind myself that time equals distance divided by rate, which is nice because it's all right here, right? It's all set up the way I want. And so I get T1 equals 2 hours. I feel good about it. Now let's try the second scenario. Then they drive 180 miles. This is their last trip, isn't it? At 60 miles per hour. Okay, T2 equals 3 hours. How fast must they drive for the last 120 miles if to have an overall average rate of 60 for the entire trip? Okay, so we know everything we need to know about trip 1, or part 1. We know everything we need to know about part 2. Part 3, we know how far they went, but we don't know how long it took, and we don't know what their rate was. So here's what we know we need. In order to get the overall average rate, we know it's the overall distance divided by the overall time, right? Well, we can find the overall distance, right? That equals 100 plus 180 plus 120. That is 400, right? And we don't know the time completely, but if we want to have an overall average rate of 60, we can solve for that, can't we? The overall time has to be equal to the distance, 400, divided by the rate. Now I'm using this again, right? That would be let's see, 60 divided by 400 is, let's do the math on that. I'm just going to do 40 divided by 6. We don't need the extra zeros. This goes in here 6 times, 36, and we get 4 left. Okay, so the time equals, I'm taking this, I'm going to leave it as a mixed number, 6 2/3 hours, right? So this we know is 6 2/3 hours. That's the total time, the overall time. We can account for 5 hours already. So that means they have to complete the third part of the trip in 1 2/3 hours in order to hit this overall average rate of 60. Does that make sense? So our last calculation which is going back here. I'll just flip and start over. our overall rate equals our overall distance divided by our overall time. We figured that out. We know that we want an overall rate of 60. We know that the distance is 400 miles. And we know that 6 2/3 is how many hours will make that work. Okay, so that's our overall time. But we're trying to find out what would be the rate of the third leg. Well, that would be the distance of the third leg divided by the time of the third leg. So that's why I did it already, but I'll do it again. We subtract the 5 hours that are legs 1 and 2, and that means that the third time has to be 1 2/3. The distance that they go in that last leg is 120 miles. So it's 120 divided by 1 2/3. And we can do 120 over 1 times, let's see, that's 3, 4, 5. I'm dividing it so I flip it, right? Which is another way of saying a compound fraction. This would be 5/3. So I multiply this by 3 over 5, and I multiply this by 3 over 5, which is exactly where I'm at right here. 5 goes into 120, what, 24 times? 24 times 3 equals 72. So R3, the rate of the third leg, is 72 miles per hour. Whoa, this one was tricky because we had to work backwards, didn't we? But if we keep our eye on the ball here and remember our formulas that D equals R times T, so T equals D divided by R, right? These three are all cousins. They're kind of triplets, right? Then that allows us to work backwards, right? We got to this, and then we worked backwards to fill in the missing piece, which was the rate of the third trip. Now, when John does these in the book, he spends a lot of time showing you the units and showing how the units will cancel. I don't want you to get too bogged down in that. I want you mostly to understand how these formulas allow us to play with all these rates and times and distances to get what we need to know. All right, I hope that made sense to you. That's a tricky calculation coming in at the end of a long lesson. So let's do the homework for today, lesson 38. I would like you to do problem 3. Oh, here comes Grace with the cold nose again. And I would like you to do problem 7. One, 2, 3, 4, 5, 6, 7. One more. Let's do 27. All right, 1, 2, 3, 4, 5, 6, 7, 8. Half the lesson. Happy Thanksgiving. I'm thankful for my students because you are killing it this year, doing such a great job. All right, thank you. That's all. Goodbye.